Okay, welcome to session 2 on digital circuit design using ADS, and we are going to get started with designing static gates. I had discussed some static gates earlier in the previous section. Now this is in continuation to that. We are going to use ADS, so we are just going to launch ADS from the start menu like this. And you can dismiss this screen by clicking on it and pressing escape. So meanwhile this goes on, let me tell you something about the PDK. This PDK has been developed by me, and there are two devices in here. One is a 130 nanometer devices, then there are 7 nanometer FinFET devices. So I'll show you those. So this PDK is called study PDK. So I'm going to say new workspace, and I am going to name the workspace as digital electronics. So that's what we are going to explore, and I'm going to attach a library. In this case I'm going to attach a study PDK library. Say OK and say create workspace. So I'm going to use a micron for layout resolution. Done. So these are the files which I'm going to use for designing. These are library files, so I'm going to put them in a library folder. So just copy all of them and just drag them to the library folder. Once this is done, I'm going to make a new folder for static gates. And in every gate I'm going to make two variations. One will be the high speed gate, other will be a low speed gate or a medium speed gate. So I'm going to again make two folders. One will be called medium speed, and then I will make another folder which I will call as high speed. Okay, so in the medium speed I'm going to right click and say new schematic, and I'm going to say not gate, and this is going to be MS, which is a medium speed. So that's my naming convention. Once I have this over here, I am going to use a library. So let me introduce you to the library. So if you look at what the library is. Okay, now this library which I have generated is for demonstration purposes and for learning purposes. So you have an NPN device here which is coming from silicon germanium process, which will be 0.5 micron silicon germanium process from IBM. So this is basically now Global Foundry. So this model I'm going to use for designing on chip temperature compensated circuits, bias circuits. Right now, then there is this section where this is a 130 nanometer MOSFET model. So there are two threshold devices. One is a high speed device which is going to be which can be operated from 1.8 volts, and the maximum voltages are around 2.4 volts. So breakdown voltage drain to source is 2.4 volts. Right, again there are two devices, PMOS and NMOS. So there are two models here. Now I have fitted BSIM 4 models for this, and I have fitted BSIM 3 models also for the same device. So I can use either of them. Mostly I'm going to use BSIM 4 model. Next is that I have got IO devices which can be which have a breakdown voltage of around 5 volts, and they can be safely operated from 3.3 volt supply voltage. Then there are some skew parameters which are basically process corners, so where you can do Monte Carlo and yield analysis on this. So this is a 130 nanometer technology file. And another thing is there are two varactors available, and these varactor diodes can be used to design VCOs. Besides that, there are 7 nanometer FinFET devices. Now I have fitted two devices which are BSIM CMG version 108 models for PMOS and NMOS. And to create this library, what I did was I did a simulation of these FinFETs, physics-based simulation in console. From that I extracted all the parameters, and I fitted the BSIM CMG model for PMOS and NMOS devices. So these are scalable models, so I'm going to use them for high-speed circuit design. So this is all about the library. So let us get started with making a very simple circuit. In this case I'm going to make an inverter. So you go to models, devices, MOS, right? So where do I find, devices, MOS, and then you can use a BSIM4 PMOS, and the source should be at the top because source is at a higher potential. So I'm going to mirror this. So this is the model and this is the device. I'm going to use I have named the model as PFET4 in my library, right? So if you remember here in the library, this model was called PFET4, right? And the other model, NMOS model, is called NFET4. Similarly, for high speed we will call it PCMG and NCMG, right? So that is the naming. Okay, so I'm going to have a length of 130 nanometer and width of 2.5 for every finger, 2.5 micrometer, and the multiplicity is 6. Now the reason for 6, okay, the reason for 6 is I will explain you when I put a NMOS device. Right, now I can clear all the parameters over here. I can only display what I want, so I'm going to display only 4 of these parameters on the display, and that's it. I can move the text by pressing F5 like this. Okay, so I have got a PMOS model. And now if I want to create an NMOS, I'm just going to do Control-C, Control-V and change this device to NMOS. Now I have a model which is called NFET4. That's what we will do, and I will change the multiplicity to be 2. So now PMOS device is going to be 3 times of NMOS device. Next is I want to clear all the text, and I want to display only those texts which I want, which are 4 of these parameters. So just like PMOS. Now the source is at the bottom. Now in this case the source is should be at the top. So I'm just going to mirror this, move the text back to where it was. Okay, so this is how the PMOS should be oriented, and this is how NMOS should be oriented. Now each of the devices is sitting in its well because this is a triple tub process. So I'm considering it as a twin tub process because I didn't model a 5-terminal NMOS device. So this is going to be the circuit for an inverter. All I'm going to do is attach pins. So the pins are going to be VDD, ground, input pin, which will be A, and the output pin, which will be Q. Okay, so very quickly I have generated the circuit. Now this circuit has got pins, so I can make a symbol for it. So once I connect all the pins, I'm just gonna say save. Once I have saved that, I can go ahead and make a model, a symbol for that. So you go to this schematic and say new symbol, and there will be a default symbol like this. So I don't like the default symbol. I want this to look like a inverter, right? So I will make my own symbol. Okay, so to make my own symbol, I'm just going to use this. Okay, so I have got Q, which would be over here. I have got A, which would be over here, sorry, and then I've got VDD, which I'm going to rotate and put it over here. Now I've got ground, which I'm going to rotate and put it over here. Now you will find that there is a grid to which this adheres to. So for present, I'm going to do the following. Okay, I'm going to reduce the pin size so that in my schematic it doesn't look awkward. Okay, and this VDD goes over here, and this ground, again the pin size I don't like, so I can reduce the pin size. And put it over here. Okay, and the ground over here. Now you'll observe that this is off grid, so I can temporarily switch off the grid and then extend this to up to here and extend this up to here, and I can put in here a bubble just to show inversion, which is this size, and I'm going to put it here, Q over here, and this I can extend. Okay, so this is my symbol for my inverter. I can turn back the grid on and just say save. So I have a symbol for inverter. Next is I'm going to test it. To test the inverter, I'm going to make a new schematic and call it test not. Okay, so once I have done test not, I can drag this device over here, and I'll have a symbol for it. I can move the text this way, right? So now I have got this. Now I don't like this, they are far away, so let me just edit this. Go back to symbol, and yes, so I'm going to move this here, and I'm going to move this here and say save, and that. Okay, so they are moved in, fine. So this is my inverter, so I'm going to attach a ground to it, and in this case I'm going to operate the entire circuit design from 2.4 volts. So I'm going to go to devices, frequency domain, 2.4 volts, or rather I can do a 2 volts or 1.8 volts. How's that? 1.8 volts is okay. So I'm going to operate from 1.8 volts for the entire designs, all the other designs also, and that's connected. So supply is connected. Next is I'm going to put here a source for putting a pulse, a square pulse, right? So I'm going to do a dynamic characteristics first, and then I'm going to look at the static characteristics, and I'm going to explain those for an inverter. Okay, so I'm going to go to sources, frequency domain, sources, frequency domain, and then there is something called pulse here, pulse. Okay, now here I specify the voltage to be 1.8 volts, and frequency is 1 gigahertz, and the width is going to be 0.5, so including rise time it will be 0.049. the rise time and the fall time are this, and this is my source, correct? And then this is going to be my load, so I'm going to put a load which is going to be a capacitor, and this capacitor I'm going to put the capacitor to be 15 femto, because this is roughly what the gate capacitance of the inverter is. So I'm loading a inverter with another inverter. This is equivalent to that. Then I'm going to name these nodes. Okay, so I'm going to name these nodes as A and B. Okay, so name node, so this would be A and this would be Q in this case. Okay, so this is done. So we are set up with this. Now what I'm going to do is I'm going to put a include file. So this is the include file which I showed you earlier. This is the PDK include file, right? This is the same file which I just showed you. So if you go down in hierarchy, you can see these are the models, and we are referring to PFET4 and NFET4. So once we are done with this, I'm going to do a transient simulation on this. Simulation transient Simulation transient, and I'm going to specify, so 1 nanosecond is the time period for 1 gigahertz, so I'm going to simulate 5 cycles, so 5 nanosecond, and the minimum step I'm going to put is 0.01 because that's the rise time of this input. Save it, hit simulate, and once you hit simulate, so I don't know why for the first time it takes so long time. Okay, once I've done that, I can display A and Q. Now, okay, so A and Q, say okay. So this is what it'll look like. This is an inversion, right? So I can zoom into any portion of the waveform, let's say here. So this one is my output, the blue one, and the red one is my input, so I'm going to make it dotted. So the red one is my input, right? So let's make it dotted line or short dash line and say okay. So this is my input and outputs. Okay, so this is behaving like an inverter, fine. I want to know what is the rise time, right? So to find out the rise time, I'm going to place a marker over here, and then I'm going to place a marker over here. So I have got two markers. One is going from 10%, so which is 0.18. So 180 pico, so 1.8 1.8 volts, right? So this is going to be 1.8 volts, and then this is going to be 1.8 minus 0.18. okay, so 1.7, 1.62. so this one, which is marker 2, should be around 1.62. so 1.7, 1.62 is not there. What I can do is I can increase the sample points. So what I can do is I can say do 1 picosecond and run the simulation again. Okay, so now I am going to locate 1.62 roughly over here, and this is going to be 1.8. okay, this is not there again, so let it be this. So now I want to see the rise time. So what I will do is I will do a delta mode. So you select the two markers and right click and say delta mode on, and the reference is going to be 1. okay, so now independent delta is this much, which is roughly minus 11, minus 12, so 16.9 pico. So you can double click this and change the format to engineering, and so 16.9 pico is the rise time, right? Same thing is I can put two markers, new, okay, one over here, new, one over here, right? So this one has to be 1.62, so roughly here, and this one is going to be 0.18 roughly there. Then again I will do a delta mode, so I'll just select this and I select this one and just right click and say delta mode on. So once you do that, I can just double click this and change the format to engineering, and I take 14 seconds as the fall time. So this is the rise time 16 seconds, fall time is going to be 14 seconds. So don't worry about the negative sign because the reference is different, right? So it's just differences. So if I subtract this from larger to smaller, so that's why it is a negative sign. Okay, so the rise time is 16.9 picosecond and the fall time is 14 picosecond. Second thing is I'm going to look at the delay. So I'm going to say marker new. Okay, place a marker here. Now this should be at half the supply. So half the supply is going to be, so half the supply is 0.9, right? So this is 0.9, and at that time what is the input? So I'm going to put this marker over here, M6, and I'm going to move M6 to be again at 0.9. So roughly at 0.9. You won't get the exact numbers. Okay. Okay. So now I'm again going to do a delta mode. So I'm going to do a select these two, right click and say delta mode on. Sorry, select these two, right click and say delta mode on, say OK. So I have a delay of, again I will do a auto to sine to engineering. So I have got a 12 picosecond of delay. So let's list this. Okay, so I have got rise time. Okay, this rise time comes out to be 16 pico, right? 16.9 pico, 0.9 pico second. Okay, similarly the fall time which I have accessed is fall time, sorry, fall time is 14 pico seconds. Okay, and then I have got a delay which will be from 50% of the input to the 50% of the output. So that would be called the delay, and that delay is going to be 12 picosecond. So this is my statistics right now. So this inverter has got a delay of 12 picosecond, right? Now I also want to see what happens to the current. Okay, so what I can do is I can put here a probe. So I can go here and say probe components, probe components, there it is, and I can put a probe here to measure what is the current drawn from the supply. The whole idea is to show you that what is the source of the loss. Okay, so this I'll call ID, and I'm going to resimulate this. And I'm going to just copy this guy. Okay, and probably I don't need all these markers, so I can delete them. And in this case I can display ID, and I will put it on the right hand side axis. Okay, just 1 second. Trying to understand what happened to the current. Okay, so that's a, it should show me 2 spikes. For some reason I'm not getting those 2 spikes. Why would that be? There should be 2 spikes, right? This is a transient simulation, right? Okay, I'm trying to show you the short circuit current. So I should be able to do that, right? Yeah, there it is. Okay, I'm going to zoom into the section which I want. So this is in milliamps, right? So I'm going to put in Q, which is the output, on the right hand side axis. Okay, so you'll see that these coincide. So these are short circuit currents. So let me put only one cycle. So let me just zoom into one cycle. So that's one cycle. So in this one cycle you are going to see two currents, right? Okay, so every cycle is, I'm going to see two pulses. Okay, so this is a short circuit current which you are seeing. Okay, this is the major source of dissipation in case of a inverter. So these spikes, right? So you can always find out what is the power dissipation due to short circuit current. So this is about the dynamic characteristics of a inverter. So now I'm going to look at the static characteristics of the same inverter. So I can create a new schematic in the same window, in the same folder. I can say test not 2, new schematic, test not 2. Okay, so in this case I'm going to keep everything as is. So this is my device under test. F5 to move the text to the right, and I am going to connect a supply of 1.8 volts. So I am going to plot the static characteristics and figure out the noise margin. So I'll just connect like this, and then here I will connect it a sources frequency domain DC, and this DC I'm gonna say is A, or rather I can say VN, doesn't matter, and I'm gonna sweep VN, right? So when I'm using a variable, so let's first do the loading. So I'm going to take a lump component, and this capacitor is 15 femto, which is the gate capacitance of the 15 femto, gate capacitance of the inverter itself. Apply, and I'm going to name one of them as Q. So this is called Q, and this as A. Right, so we are ready with this, and I am using a variable, so I have to declare it. So I am using one variable called Vin, and then I have to place the include file, and I have to do simulation DC, simulation DC. So I am going to do a DC simulation. Here I am going to sweep Vin from 0 to 1.8 volts, 0 to 1.8 volts in steps of 0.001 volt. Sorry for the typing mistake, and say OK. So I'm ready with this, and what else do I need? Nothing. So I can hit simulate. Okay, once I have simulated, I can plot V out, add versus A. So that's going to be the transfer characteristics. Now let's try to understand what is this transfer characteristics. Okay, first of all I want to find out the trip point. The trip point is when V out equal to Vin, right? So I'm going to make another equation for a line. Okay, and that equation I will call V out is equal to V in. Okay, and then I'm going to plot V out over here. Okay, so it doesn't come versus samples, it comes versus samples, so that's not right. So what will I do? V out is equal to this versus V in okay, So let's do this way. V out is equal to A. Okay, now it's okay. Okay, so double click it in this. So this intersection point, which is at 0.9, is the trip point. So what it means is that this is a symmetric inverter. Now if I resize these transistors, then it will no longer remain symmetric, right? So symmetric inverter is when the pull up and the pull down is with the same current. So the trip point is going to be the center, or the V out equal to V in is the trip point, and that is at the center of the VDD range. So that is called the trip point. Now if this trip point is not at the center, it will be asymmetric, and this is symmetric just because we have done the scaling here. So the scaling is PMOS is 3 times of NMOS. This is because the whole mobility is 3 times the electron mobility. So if I size the PMOS to be 3 times the NMOS, the current which is going to do a pull up is going to be the same current which is going to do the pull down. So then the rise and fall times are going to be more or less symmetric, and this static characteristics are going to have a trip point at the center. Now let's see what is the effect of changing the size, right? So what I do is, on this width, I am going to declare a tune. Okay, so I am going to change this width from, let's say, 1 to, so right now it's 2.5, right? So 1 to 4. Okay, so now this is tunable now, though default value is 2.5. So it is for a symmetric, it is 2.5 into 6, and it is 2.5 into 2. So this is 3 times of this. So now let's run simulation tune mode. So go to tune mode. Done. So this is my gate which I can scale. So if I look at the output is like this. Okay, so now what I'm going to do is I'm going to store this state, and this I will call as symmetric. Okay, and then I'm going to change this to this value. So basically you can see now. Okay, then I'm going to say store this as plus. So here PMOS basically is bigger than the NMOS. So basically pull up current is more than the pull down current. So the entire curve moved to the right. Okay, and then I am going to move this down. So this is the other side. So this I'll call as minus. Okay, so let's just change this. So this is going to be the nominal. Okay, and this one is going to be the plus, and this one is going to be the minus, dash, dash. Okay, so what I'm showing you here is this is a symmetric. Red one is a symmetric inverter. Now blue one and this brown one, or rather green one, is an asymmetric inverter. And why they are asymmetric? Because the ratio of PMOS and NMOS is not 3 times, right? Where the pull up and pull down currents are now not even. So that's why the trip point changes either to be a higher value or a lower value. So this is called asymmetric inverter. Okay, so now you understand that why that scaling was 3 times, right? Okay, so what I'm going to do is I'm just going to quit this and quit this without doing any update. Now, so I'm back to where I was, right? This is where this is a symmetric response of a symmetric inverter. Okay, now I want to find out what are the noise margin. Okay, so what I'm going to do is I'm going to declare Q. Okay, so basically I'm going to do a derivative of it. So I'm going to do an equation. I'm going to say SLP is the slope is differential of Q. Now when I do that, okay, so there is a double F, sorry, okay, it's a differential of Q. I'm going to plot the differential of Q. Equation, that's the slope. Now you will notice that this slope becomes -1 at some point, right? Okay, so this slope will become -1 at some point. So let's put here a marker. Okay, so this is the slope. Let's find out a point where it becomes -1. Okay, so it becomes -1, and similarly on the other side I want to find out where this slope becomes -1. Now this is the slope of this transfer characteristics, right? So I'm going to impose on that. So this will become -1. So roughly over here, right, this is -1. Now I'm going to also plot here the output, which is Q versus A. Traces of different lengths. Okay, don't worry about it. Put it on the right hand side axis. Okay, so now this is my transfer characteristics, correct? So now this intersection point is occurring at, okay, so these intersection points are occurring at 0.7 here and 1.041 here. So basically this distance from here to here, this is called lower noise margin, and here to here this will be called the higher noise margin. So noise margin high and noise margin low. So this is going to be 0.7. so basically NMH is equal to independent. Okay, you cannot do this on this one, so let's just type it out. 0.732. so this is the noise margin high and the noise margin low. So why it's called high is because the input range for which the output is high, that's why it's called noise margin high. Okay, then you have got noise margin low. So that noise margin low will be equal to 1.8 minus whatever that value is, 1.041 minus 1.041. so that's going to be noise margin low, and the overall noise margin will be the average of the two. So the noise margin is going to be noise margin high plus noise margin low in bracket divided by 2. Okay, so now I'll put that noise margin over here as equation noise margin, and I will remove the independent value. Okay, so the noise margin is 0.7 volts. Okay, so the noise margin is 0.7 volts. So this is the static characteristics of NMOS. Now let's see, there are different regions here. Okay, the region between here, so this region, okay, between this 0.732 to 1.04, this is a high gain region, and the highest gain is at the trip point, right? So this is the transfer characteristics. Now let's see what happens over here. Here what is happening is, as the input voltage is low, the NMOS device is off and the PMOS device is on. Now going from here, what has happened from here to here, which is from, let's say, 0.28 volts is the threshold voltage of the NMOS. So at that point the NMOS turns on, and the PMOS, so NMOS is in the triode region and the PMOS is in the saturation region. So this is the second region. The third region is when NMOS and PMOS are both on and they are in the saturation region. And from this point, which is 1.048, to almost this point, which is 1.43236, in this region the PMOS is in the triode region and the NMOS is in the saturation region, and beyond this the PMOS is off and the NMOS is on. So there are 5 regions in here in the transfer characteristics of a inverter. Now besides this, you should know what are the losses. Okay, so as we have seen in the dynamic characteristics, so let's look at the dynamic characteristics. Okay, so there is a short circuit current. Whenever there is a transition, there is a short circuit current. So if you take the half base into height, okay, so you'll find the area under the curve. So that would give you the total current which will be drawn from the supply times the supply voltage. So that will give you the dynamic loss. The other cause of loss is the static loss, and there are 3 leakages which are important for this static loss. One of them, the dominant one of them, is the subthreshold leakage. Okay, so if you study the device, you will note that the static loss comes from the subthreshold leakage, and then there is a PN junction diode leakage to the bulk. That's the other source, and then there is a what you call hot carrier injection current. That is the third cause of the leakage. So there are 3 leakages which cause the static loss. Okay, one is the current due to subthreshold leakage of the device, which is a dominant one. Then there is a PN junction leakage, reverse bias leakage of the drain to bulk diode, and then there is a hot carrier injection leakage current in the in the devices which are short channel devices. You see that leakage is the other cause of the static loss. Now in dynamic losses, there is one charging and discharging of the output capacitance. So basically, if you see the schematic, this capacitor is being charged by a pull-up device, and then it's discharged by a pull-down device. So now the half of CV square, right? Half of CLV square would be the loss when you are charging it, and then half of CLV square would be the loss when you are discharging it. So the total loss is going to be CLVC square times of frequency. So that is going to be the total loss because of charging and discharging, which is a dominant component. The other component of the dynamic loss is going to be the short circuit current. Now if the time is so small, the rise time and fall time, then the short circuit current is going to be small. So this is not going to be the dominant dynamic loss. The dominant dynamic loss will be charge and discharge of this capacitor. Okay, so now here I am explaining you what's a static loss, and I have explained you what is the source of a dynamic loss, and I have explained you how I did the noise margin, right? Roughly these are the empirical formulas for the noise margin. And here is I'm showing a current loss due to here is the loss due to the short circuit current, right? And here is a loss, total dynamic loss, which has this loss which is due to the charging and discharging of the capacitor. So this is the dominant one. So there are dynamic losses and then there are static losses. So this basically finishes this session on inverter analysis in CMOS inverter in ADS. So I'm going to stop here for this session, right?